Let's begin with the number 792 kilometers per second. That is the speed of light in empty space. It's such a large number that it almost loses meaning. If I say a car moves at 100 kilometers per hour, you can picture that. If I say a jet moves at 900 kilometers per hour, you can stretch your imagination. But 792 kilometers in a single second. In one heartbeat, light could circle the Earth more than 7 times. It could travel from the moon to Earth in just over a second. This is not just fast. It is beyond the scale of ordinary human experience. But the real reason this number matters has nothing to do with speed in the usual sense. It matters because this number appears to be woven into the structure of reality itself. It is not merely the speed of light as a substance. It is the maximum speed at which anything, matter, energy, information, cause, and effect can travel through the universe. It is less like a traffic rule and more like a boundary built into space-time. Now here is where things become unsettling. As you move faster and faster, approaching this cosmic speed limit, something begins to happen to time. Not metaphorically, not as an illusion, measurably, predictably, reproducibly. Time slows down. If you are standing still relative to me, we agree on how fast our clocks tick. But if you climb into a spacecraft and accelerate to an enormous fraction of the speed of light, and I remain on Earth, I will measure your clock running slower than mine. From your perspective inside the spacecraft, everything feels normal. Your heartbeat is steady. Your thoughts flow at the usual pace. Your wristwatch ticks calmly. But when you return and we compare clocks, yours will show less time has passed. At first, this sounds like a mechanical problem. Maybe the clock malfunctioned. But we have tested this with the most precise clocks ever built, atomic clocks, and they behave exactly as predicted. Time itself stretches when motion increases. Why should speed affect time? That is the question that forced physics to grow up in the 20th century. For centuries, we assumed time was universal. One great invisible river flowing evenly everywhere. The same second ticking on Earth, on Mars, in distant galaxies. It felt obvious. It felt necessary. But nature does not consult our intuitions. Experiments revealed something deeply uncomfortable. The speed of light is always measured to be the same, no matter how fast the observer moves. That stubborn fact forces space and time to adjust themselves. If the speed of light refuses to change, then something else must give way. And what gives way is time. As you approach 792 kilometers per second, the slowing of time becomes more dramatic. The effect is tiny at everyday speeds, but it grows relentlessly. And if you imagine reaching the speed of light itself, which, as we will see, massive objects cannot, the mathematics says time would stop entirely. That is what people mean when they say time starts dying at light speed. Not that clocks shatter or reality collapses in fireworks, but that the ticking of time depends on motion. The faster you move through space, the slower you move through time. At the ultimate speed limit of the universe, motion through time would shrink to zero. This number is not just large, it is a clue. A doorway into the strange geometry of space-time, where speed reshapes duration and motion bends the flow of moments themselves. In the early 20th century, physics was in a strange position. The equations describing electricity and magnetism were working beautifully. They predicted that light is an electromagnetic wave and that it travels at a specific speed, 792 kilometers per second. But there was a problem. According to older ideas about motion, speeds should depend on the observer. If you run toward a sound wave, you measure it moving slightly faster relative to you. If you run away, it appears slower. That's simple addition of velocities. It works for cars, balls, airplanes, everything in daily life. So scientists naturally assumed light would behave the same way. If you chase a beam of light, shouldn't you measure it moving slower relative to you? Experiments were designed to detect differences in the speed of light, depending on Earth's motion through space. The expectation was simply, since Earth orbits the Sun, and the Sun moves through the galaxy, the measured speed of light should shift slightly depending on direction. But every careful measurement gave the same stubborn result. The speed of light was always the same. It didn't matter if the source was moving or the observer was moving. The number refused to change. This was deeply unsettling because it seemed to contradict common sense. Motion had always been relative. If a train moves past a platform, passengers see the platform moving backward. People on the platform see the train moving forward. Both descriptions are valid. Speeds depend on who is measuring, but light was different. It behaved as if it had access to a deeper rule. This is where Albert Einstein made his radical move. Instead of trying to modify the equations of light, he asked, what if the equations are right, and our assumptions about space and time are wrong? He started with two simple principles. First, the laws of physics are the same for all observers moving at constant speeds. Second, the speed of light in vacuum is the same for all observers, no matter how they move. If you accept those two statements together, something extraordinary follows. Imagine you are on a fast-moving train and you shine a flashlight forward. According to the old way of thinking, someone standing on the ground should measure the light's speed as the speed of the train plus the speed of light. But experiments say no. Both you and the person on the ground measure exactly 792 kilometers per second. If speeds don't add the usual way, something else must adjust to make the math work. That something is time and space. Einstein realized that measurements of length and duration must depend on motion. Two observers moving relative to each other will not agree on distances or time intervals. They will disagree not because one is mistaken, but because reality itself allows different measurements depending on motion. Time, which had been treated as universal and absolute, becomes flexible. Consider two lightning strikes hitting the ends of a moving train. An observer standing on the platform might see them occur simultaneously. But someone inside the train, moving relative to the platform, may see one strike before the other. Both observers are correct in their own frames of reference. Simultaneity itself is no longer absolute. This is the quiet revolution of special relativity. It doesn't smash clocks with drama. It simply removes the idea of a single cosmic clock governing the entire universe. Instead, each observer carries their own time, shaped by their motion. The fixed speed of light forces space and time to reshape themselves so that its value never changes. That reshaping is not an illusion or a trick of measurement. It is built into the geometry of space-time. And once you accept that, the slowing of time near light speed is no longer shocking. It becomes inevitable. Now imagine time not as a uniform river flowing at the same rate for everyone, but as something that can stretch and bend depending on motion. Think of it like a budget. Every object in the universe has a finite motion budget. And that budget can be spent moving through space or moving through time. But the total always adds up to the same amount. When you are standing still relative to your surroundings, all of your motion is directed through time. Your days pass normally, your heartbeat ticks steadily, and your wristwatch advances second by second. But the moment you start moving through space, a portion of that motion must be diverted from time. The faster you move, the more you are spending motion on traveling through space, and the less remains to move forward through time. At everyday speeds, this effect is imperceptible. When you ride in a car at 100 kilometers per hour, the difference in how your clock ticks compared to someone standing still is unimaginably tiny. It is so small that our brains cannot even detect it. But as your speed increases toward a significant fraction of the speed of light, the effect grows dramatically. Your heartbeat slows slightly relative to a stationary observer. Seconds pass differently. Minutes stretch. Hours begin to lag. And as your speed approaches 792 kilometers per second, the effect becomes extreme. The ticking of your clock would slow down more and more until, at the speed of light itself, it would stop entirely. From the perspective of a photon, no time passes at all. Its journey from a distant star to Earth, which may take thousands or even millions of years from our perspective, is instantaneous from the photon's point of view. This is not science fiction or metaphor. It is a consequence of the geometry of space-time. Time and space are not separate entities. They are intertwined dimensions, forming a four dimensional fabric in which all events occur. When we move through space at high velocities, we are effectively tilting our path through this fabric. That tilt reduces the component of our motion through time. The total motion through space-time remains constant. It's just redistributed. In other words, the universe enforces a strict accounting system. The faster you go through space, the slower you must go through time. Massive objects like spaceships or planets cannot reach the speed of light, because doing so would require infinite energy. As an object accelerates, its effective mass increases, making further acceleration progressively more difficult. This is why no spacecraft, no matter how advanced, could ever allow a human to experience life at light speed. Photons are massless, which is why they can travel at this ultimate speed, experiencing no passage of time along the way. This thought experiment also helps us understand why time is relative and personal. If two observers travel at different speeds and then compare clocks, they will see different amounts of elapsed time. Neither is wrong. The universe simply does not provide a single, absolute measure of time that applies to everyone. This challenges every intuition we have about how the world should work. We are used to thinking of time as fixed and universal, but at high velocities, it becomes fluid and observer-dependent. Reality stretches in ways that are invisible to our slow, moving brains, but mathematically inevitable and experimentally verified. Time dilation, as this effect is called, is not just a curiosity, it has practical consequences. Satellites in orbit experience tiny amounts of time dilation that must be corrected to ensure GPS signals remain accurate. Particle accelerators routinely observe particles that decay more slowly as they approach light speed, exactly as relativity predicts. Time itself is bending to preserve the cosmic speed limit, demonstrating that the universe is far stranger than our daily experience suggests. This bending of time is a window into the deeper structure of reality, a glimpse of the hidden rules governing motion, energy, and existence itself. Now let's consider what happens when you try to push an object with mass closer and closer to the speed of light. At first, acceleration feels familiar, like pressing your foot harder on the gas pedal of a car. The vehicle speeds up, covering more distance per second. But as you approach a significant fraction of light speed, physics begins to behave in ways that are profoundly counterintuitive. The faster you go, the harder it becomes to go even faster. This is not a mechanical limitation of engines or fuel. It is a fundamental law of the universe. According to Einstein's equations, as an object moves faster, its relativistic mass increases. That is, from the perspective of a stationary observer, the object becomes heavier. The energy required to continue accelerating grows without bound. To reach the speed of light itself would require an infinite amount of energy, which is impossible. No machine, no rocket, no civilization, no matter how advanced, could supply infinite energy. The speed of light is an absolute boundary in the cosmos, not just a guideline. This explains why massive objects can never experience the extreme effects of time stopping completely. Only massless particles, like photons, can travel at light speed. They experience no passage of time because their motion is entirely through space, with no component left for motion through time. From the perspective of a photon, the moment it leaves a distant star and the moment it reaches Earth are simultaneous. No seconds elapse, no minutes pass. The journey is instantaneous. This is why astronomers can observe light from galaxies billions of light years away, while understanding that for the light itself, there is no experience of time at all. It is traveling not just across distance, but through the fabric of space-time in a unique way that defies our normal understanding of duration. To visualize this, imagine a flashlight inside a spaceship moving at an enormous fraction of light speed. You switch it on and shine the beam across the cabin. Inside the ship, everything appears normal. The light moves from one end of the cabin to the other as usual. However, an observer outside watching the ship streak past sees the light following a diagonal path because the ship is moving forward while the light moves across it. Despite these differences in observation, both the observer inside and the one outside must measure the light moving at the exact same speed, 792 kilometers per second. To reconcile this, time and space must adjust. Inside the ship, time ticks more slowly relative to the outside observer, and distances contract in the direction of motion. Space and time are flexible, reshaping themselves to ensure the cosmic speed limit is never violated. This adjustment of time is not an illusion or a measurement error. It is a real physical effect, repeatedly confirmed through experiments. Particle accelerators routinely accelerate subatomic particles to speeds incredibly close to light speed. The faster these particles move, the longer they live before decaying. Their internal clocks slow down in exact accordance with the predictions of relativity. Similarly, GPS satellites orbiting Earth experience tiny but measurable differences in time compared to clocks on the ground. If engineers did not account for time dilation, your GPS would be inaccurate by kilometers within a single day. The universe enforces this subtle accounting, and the consequences are observable in both the laboratory and the technologies we rely on every day. These phenomena demonstrate that time is not an absolute, universal parameter flowing identically for all observers. Time is intimately linked with motion, energy, and the structure of spacetime. The closer an object moves to the speed of light, the more extreme the effects on time become. Clocks slow down, journeys stretch, and durations measured by different observers diverge. The laws of physics are consistent, but our human intuition struggles to grasp them because we evolved in a world where speeds are slow and relativistic effects are negligible. Approaching light speed exposes the hidden geometry of the universe, revealing that time is not a separate entity, but a dimension woven together with space, constrained by the ultimate cosmic speed limit. Let's take a step further and explore how this plays out in thought experiments, which allow us to imagine scenarios that reveal the underlying principles of reality. Consider yourself inside a perfectly sealed spaceship with no windows and no external reference points. You turn on a flashlight and shine it across the cabin. Inside the ship, everything behaves normally. The light moves from the front of the cabin to the back at its usual speed. Your perception of time remains unchanged. The seconds tick steadily on your clock, and your movements feel ordinary. Now imagine your spaceship begins to accelerate to an enormous fraction of the speed of light. Inside, you still feel weightless, and every internal measurement seems normal. Your flashlight beam still crosses the cabin at the speed of light relative to you. There is no feeling of time slowing down from your own perspective. Yet an outside observer, watching your spaceship race past, would see the beam follow a diagonal path. While the light moves across the cabin, the spaceship moves forward. This creates a longer path, and yet the observer must still measure the light moving at exactly 792 kilometers per second. To reconcile this, time itself adjusts. The internal clock on your ship ticks more slowly relative to the outside observer, and the dimensions of the ship contract slightly along the direction of motion. Space and time cooperate to preserve the universal speed of light. This is not a trick of perception. It is an actual physical effect embedded in the geometry of space-time. This concept challenges intuition because we are not accustomed to living in a universe where the fabric of reality bends in response to motion. At human speeds, these effects are minuscule and imperceptible. A car driving at 100 kilometers per hour experiences time differences that are too small to measure. But at velocities approaching light speed, these effects dominate. Time slows drastically. Seconds for you might pass as hours for someone at rest, and years of travel could amount to only moments from your perspective. This is the essence of time dilation, one of the most verified predictions of special relativity. Atomic clocks flown on high-speed aircraft or placed in orbit consistently demonstrate these effects, and particle accelerators routinely measure subatomic particles, living longer as they approach light speed. Each of these examples confirms that the universe enforces a strict relationship between motion through space and motion through time. Now, consider the role of mass in this framework. The faster a massive object moves, the more energy is required to continue accelerating it. Unlike photons, which are massless and can traverse the cosmos at light speed without experiencing time, massive objects face an insurmountable barrier. As an object approaches the speed of light, its effective mass increases toward infinity, and the energy needed to accelerate it further grows without limit. This is why no spacecraft, no matter how technologically advanced, could ever reach or exceed the speed of light. Nature imposes this limit not arbitrarily, but as a fundamental consequence of the geometry of spacetime. Light's constant speed is not merely a number. It is a rule built into the universe itself. It governs how energy, mass, space, and time interact. This framework also reshapes our understanding of simultaneity. Two events that appear simultaneous to one observer may occur at different times for another observer, moving relative to the first. There is no universal now. Time is personal, observer-dependent, and intimately tied to motion. Clocks no longer simply measure the passage of seconds. They measure time along a particular trajectory through space-time. Light, moving entirely through space with no motion through time, represents the extreme of this principle. It demonstrates that time is flexible, relative, and inseparable from the structure of the universe. It is this bending, this intimate connection between motion and temporal flow that allows the universe to maintain its cosmic speed limit consistently across all observers, no matter how fast they move. Time is no longer a passive stage upon which events unfold. It is a dynamic, responsive dimension intertwined with space, energy, and motion. Understanding this principle is essential to grasp why approaching light speed transforms the very experience of time itself. Humans struggle to grasp the true nature of time because our brains evolved in a world of slow motion, where relativistic effects are negligible. For thousands of generations, humans experienced movement at walking speeds or in simple vehicles. The laws of Newtonian physics were sufficient to explain daily phenomena. If you throw a rock, jump from a ledge, or row a boat, time seems absolute, the same for everyone, everywhere. Our intuitions about cause and effect, simultaneity, and duration are built on this slow-moving world. When confronted with speeds approaching 792 kilometers per second, the universe behaves in ways that directly contradict these intuitions. The idea that two observers moving at different speeds could measure entirely different durations for the same event is deeply unsettling. The human mind resists it because it challenges every mental model we have constructed to survive in a world of moderate velocities. Even professional scientists initially struggled to internalize relativity. Einstein himself described the thought experiments that led to his discoveries as playful yet profound. He imagined chasing a beam of light or riding alongside it, and then asked how clocks and rulers would behave under those conditions. These exercises revealed that time could not remain absolute if the speed of light was constant for all observers. The realization required abandoning centuries of entrenched assumptions about a universal clock ticking identically for all observers. To accept relativity fully, one must rethink the very nature of measurement, simultaneity, and reality itself. Part of the difficulty lies in the fact that relativistic effects are invisible at everyday speeds. A car, a plane, or even a spacecraft moving at tens of thousands of kilometers per hour experiences time differences that are minuscule. They are so small that, without highly precise instruments, they are undetectable. Our senses evolved to operate at human scales, and our intuitions about time, space, and motion are tuned accordingly. When confronted with situations where these differences become substantial, such as near light, speed travel, or extreme gravitational fields, our mental models break down. Time no longer behaves as a uniform river. It bends, stretches, and flows differently depending on velocity and gravitational influence. Accepting this requires more than memorizing equations. It requires a conceptual leap into a universe that operates according to principles alien to our everyday experience. Another source of struggle is the human attachment to causality. We instinctively believe that effects follow causes in a clear, linear sequence. Relativity preserves causality but does so in a way that is counterintuitive. Events that seem simultaneous to one observer may occur in a different order for another. This does not violate logic or physics, but it challenges the deeply ingrained notion of a shared universal now. Every observer has their own timeline, their own measurement of duration, and their own sequence of events. Grasping this requires disentangling our subjective experience from the objective structure of spacetime, which is a subtle and often uncomfortable process. Finally, humans struggle because time itself is abstract. Unlike space, which we can perceive and measure with rulers, time is intangible. We experience it through change, motion, and memory, but its flow is invisible. Relativity exposes the fact that this flow is not absolute. It depends on motion and perspective. Understanding that time can stretch slow and even stop for a fast-moving observer challenges our most fundamental experiences of reality. Our brains resist it because it undermines the intuitive scaffolding upon which we have constructed our understanding of the world. Yet, despite our discomfort, experiments confirm it repeatedly. Particle accelerators, atomic clocks, GPS satellites, and observations of cosmic phenomena all demonstrate that time is flexible, relative, and inseparable from the motion and geometry of the universe. Accepting this reshapes our view of reality, demanding a deeper, more nuanced understanding of what it means to exist within spacetime. Time does not in the dramatic sense that clocks shatter or reality collapses. From the perspective of an observer moving with an object, time always feels normal. A person inside a fast-moving spaceship experiences their heartbeat, thoughts, and every second as usual. The slowing of time is always relative to another observer. If someone remains on Earth watching the spaceship speed past, they will measure the traveler's clock ticking more slowly than their own. This is not an error or malfunction. It is the universe revealing that time is not absolute. Each observer carries their own measure of time, dependent on their motion and perspective. Time becomes personal, not universal, and this realization fundamentally changes our understanding of reality. Relativity demonstrates that time and space are intertwined, forming a four-dimensional fabric called spacetime. Each object moves along its own path through spacetime. The faster an object moves through space, the less it progresses through time. This relationship is not metaphorical, it is a measurable physical effect. Light, which moves entirely through space at 792 kilometers per second, has no passage of time from its own perspective. A photon emitted by a star billions of light years away arrives at Earth instantaneously in terms of its own existence. For massless particles, the concept of time along their trajectory is meaningless. This illustrates the extreme case of time dilation and the intimate connection between motion and temporal progression. The absence of a universal clock means that simultaneity is relative. Two events that appear simultaneous to one observer may occur in a different sequence for another observer moving relative to the first. This challenges the intuitive notion that there is one objective timeline for all events in the universe. Each observer constructs their own timeline based on their motion and frame of reference. The lack of a shared no requires a conceptual shift from the traditional view of a linear absolute time. Time is no longer a passive stage upon which events unfold, but a dynamic, flexible dimension influenced by motion, energy, and the geometry of space-time itself. The personal nature of time has practical consequences as well. Satellite systems such as GPS must account for differences in time experienced by clocks in orbit compared to those on Earth. Even small discrepancies, invisible to the human eye, accumulate quickly and can result in errors of kilometers if left uncorrected. Particle accelerators exploit time dilation to study subatomic particles. Particles moving near light speed decay more slowly than their stationary counterparts, confirming predictions of special relativity. These examples show that time dilation is not theoretical or abstract. It is a real phenomenon that governs physical processes and technological systems alike. Time is flexible, and its flow is dependent on motion through space and the observer's frame of reference. Understanding that time is personal also requires confronting deep philosophical questions. If each observer experiences a unique timeline, then our notion of past, present, and future is relative. What we consider the now is a localized slice of spacetime, not a universal instant shared with distant stars or galaxies. The flow of time is linked to the motion of objects and the structure of spacetime, rather than being an independent entity. Relativity forces us to abandon the comforting idea of an absolute, uniform clock ticking everywhere. Instead, the universe presents a network of intersecting timelines, each valid within its own frame of reference. Accepting this changes our perception of reality, emphasizing the interdependence of motion, space, and time. It is a profound shift from everyday intuition, yet one confirmed by precise experimentation and observation, demonstrating that time is not absolute, but a relative, observer-dependent dimension that shapes the universe itself. Relativity provides a remarkably precise and consistent framework for understanding how time behaves at high speeds. Yet it does not answer every question about the nature of time itself. While we can predict how clocks slow down when moving near the speed of light, or how particles decay more slowly in particle accelerators, we still do not fully understand what time fundamentally is. Is it an emergent property arising from deeper physical laws? Is it a fundamental component of reality like space, energy, or mass? Attempts to unify relativity with quantum mechanics highlight this uncertainty. At the quantum scale, particles can exist in superpositions, interacting in ways that seem to disregard classical notions of cause and effect, while general relativity treats time as a continuous, smooth dimension intertwined with space. Combining these two descriptions into a coherent theory of quantum gravity remains one of the greatest unsolved problems in physics. This shows that although we can describe the behavior of time with incredible accuracy under certain conditions, its ultimate essence remains elusive. Even with our experimental confirmation of time dilation, length contraction, and the constancy of the speed of light, questions linger. Why does the speed of light have the exact value it does? Why is there a universal speed limit built into the fabric of spacetime? These numbers are not merely arbitrary, they encode fundamental relationships between space, time, energy, and mass. Yet the reason for their specific magnitudes is still a mystery. Physicists can measure them, include them in equations, and build technologies around them, but the deeper why remains hidden. The constancy of the speed of light dictates the structure of space-time itself, determining how events unfold relative to different observers. Yet understanding the ultimate origin of this constant is one of the most profound unsolved problems in science. The limits of our understanding also extend to extreme environments, such as black holes or the early universe. Near a black hole, space-time is so strongly curved that time effectively comes to a standstill relative to a distant observer. What does this imply about the flow of time for matter inside the event horizon, or for hypothetical travelers approaching it? Similarly, the Big Bang represents a state in which conventional notions of time may break down entirely, challenging the very framework we use to understand events and durations. Our equations give us partial answers, but at singularities and quantum extremes, they fail, reminding us that our grasp of time is incomplete. Another layer of uncertainty comes from the philosophical implications of relativity. If time is personal and observer-dependent, then there is no single timeline governing the universe. Past, present, and future are not absolute. They depend on the observer's motion and perspective. This raises questions about determinism, free will, and causality. While physics preserves causal order within any frame of reference, the relative nature of time challenges our intuitive understanding of cause and effect. It forces us to rethink reality, not as a single narrative unfolding uniformly, but as a web of intersecting experiences, each valid within its own context. Despite these unknowns, relativity gives us extraordinary predictive power. We can send probes across the solar system, track GPS satellites with precision, and explore particle physics in ways that depend critically on the flexible nature of time. Experiments repeatedly confirm the stretching and contracting of time as velocities approach light speed. Yet the fact that we can describe these phenomena mathematically and observe them experimentally does not equate to fully understanding the essence of time itself. It remains a concept that is deeply tied to the universe's structure, intimately linked to space, motion, and energy, but ultimately still a profound mystery, waiting for a deeper theory to reveal its true nature. Time behaves in ways that are predictable yet fundamentally counterintuitive. We can manipulate it conceptually, measure it with precision, and see its effects in the real world. Still, the ultimate origin, meaning, and full nature of time remain beyond our current reach. It is a realm where physics meets philosophy, where observation, mathematics, and imagination converge, leaving us with both extraordinary knowledge and enduring mystery. Understanding that we do not yet fully grasp time is not a limitation, but an invitation to explore reality more deeply, to question assumptions, and to embrace the universe's subtle and astonishing complexity. Every object in the universe moves through space-time at a total speed that is constant when measured in a four-dimensional sense. This idea can be visualized as each object traveling along a path through space-time, with motion divided between the dimensions of space and time. When an object is at rest relative to its surroundings, all of its motion is directed along the time axis. Seconds pass normally, minutes tick steadily, and the object experiences the full flow of time. As the object begins to move through space, some of that motion is diverted from time into space. The faster it moves, the greater the portion of motion devoted to spatial displacement, and the smaller the portion remaining for progression through time. This redistribution is not an arbitrary rule. It is dictated by the geometry of space-time and the constancy of the speed of light. The total magnitude of motion through space-time remains unchanged, but its components shift between space and time as speed varies. Light represents the extreme case of this principle. A photon is massless and moves entirely through space, leaving no motion for the time dimension. For light, time does not advance. From the moment it leaves its source to the moment it is absorbed, no time elapses from its own perspective. This is why a photon emitted from a galaxy billions of light years away reaches Earth instantaneously in its own frame, despite taking billions of years from our perspective. The behavior of light demonstrates the intimate link between motion through space and the flow of time. Time is not a universal river. It is a dimension that flexibly responds to how objects move through space-time. This concept is not limited to abstract mathematics. It has practical consequences and experimental confirmations. Atomic clocks flown on high-speed jets or placed on satellites orbiting Earth consistently show time dilation effects exactly as predicted by special relativity. Particles accelerated to near light speeds in laboratories live longer than they would at rest, confirming that the rate of time passage depends on velocity. GPS systems, which underpin navigation for billions of people daily, require adjustments for relativistic effects to maintain accuracy. Without accounting for time dilation, satellite-based positioning would drift by kilometers each day. These examples show that time is not merely a conceptual tool. It is a measurable, physically real phenomenon that bends and stretches in response to motion through space-time. The geometry of space-time also reshapes our understanding of simultaneity and sequence. Two events that appear simultaneous to one observer may occur at different times for another observer, moving at a different speed. There is no universal no that applies to the entire universe. Each observer carries a unique measure of time, valid within their frame of reference. This challenges human intuition, which evolved in a slow, moving world where differences in relative motion were negligible. At everyday speeds, time appears universal and uniform, but at velocities approaching the speed of light, its relativity becomes undeniable. Accepting this requires a conceptual shift. Time is local, personal, and inseparable from motion. The universe enforces this relationship between space, time, and motion through its fundamental structure. The constancy of the speed of light acts as a guiding principle, dictating how motion is distributed between space and time. This principle ensures that no object with mass can reach light speed, and that the laws of physics remain consistent across all frames of reference. The bending of time, the slowing of clocks, and the contraction of space along the direction of motion are all manifestations of a deeper order, a cosmic accounting system that maintains consistency and preserves causality. The universe is not chaotic. It operates according to precise, elegant rules that are revealed when we observe phenomena at extreme velocities. Time is not merely a backdrop for events, but an active, dynamic dimension intertwined with space, motion, and energy. Each trajectory through space-time carries its own temporal rhythm, and light shows the ultimate limit, a path entirely through space with no passage through time. Understanding this principle reshapes our perspective of reality. The flow of time is not universal, not absolute, and not guaranteed. It is a consequence of motion through the universe's four-dimensional fabric, an intimate feature of the cosmos that demonstrates both the predictability and the profound strangeness of space-time. Every observer traces a unique path, experiencing their own sequence of events, highlighting the personal and flexible nature of time itself.